Okay, so let's pick this up on thinking about the global budgets of energy in the atmosphere and ocean and Earth system broadly, but we're going to try and link them up particularly to what's going on in the ocean because that's our primary target. So we thought a little bit about how estuaries walk. We thought a little bit about how numerical grid cells work. We're noting volume flows in and out. We're noting salt flows in and out. We're noting temperature flows in and out. We're thinking about the conservation principles of both the differential equations that relate the material derivatives, so stuff like temperature and salinity following the motion of a fluid, to the Eulerian coordinate system, that is temperature and salinity flowing past a point, and then integrating those differential equations over a control volume like this estuary, or a control mass like a little hunk of water that's moving around. And when we do that, we're able to express the budgets that we might want to think about. So what about the Earth as a whole? What does its energy budget look like? All right, this is a classic illustration from Kevin Trenberth and lots of collaborators. It gets updated about every 5 years or so. This version happens to be from 2009. There's one later version that has a few more digits of precision on some of these numbers. But this is what the global energy budget looks like for the Earth system. So let's see what's going on at the top of the atmosphere up here. Here's the incoming solar radiation. And this is 341 watts per meter squared, and it's watts per meter squared of the surface of the Earth, the surface of the top of the atmosphere, exactly. That's what the meter squared is. So that's how much energy is coming on. And then let's see what's going out. Well, part of it's getting reflected back out. That's the effects of albedo. It's a big hunk of that is bounced off of the clouds and the atmosphere itself. Never makes it down very far. Never sees the ocean. So 79 watts per meter squared goes right back out. And then 23 watts per meter squared bounces off the surface, which is partly ocean and partly land. And if there's sea ice, more of it bounces off. If there's not sea ice, more of it's absorbed. If there's snow on the ground, more of it's reflected. If there's not snow on the ground, more of it's absorbed. So this is a sensitive metric that changes with the climate. But on average, in today's present day Earth, about 102 watts per meter squared of the 341 goes back to space. And all three of these are actually measured directly by satellites. So these are pretty clean numbers, both in mean and variability. The remainder that's not reflected by the surface or clouds gets absorbed by the surface. That could be by land or by ocean. We'll come back to that in a minute. Okay, once energy is absorbed, or it could be absorbed by the atmosphere, this little branch over here. Once the energy is absorbed by either the atmosphere or the ocean, it makes that, or the land, it makes that sphere warm, and then that warm sphere starts producing energy fluxes of its own. One thing that it does is it produces outgoing long wave radiation. So if the sun is like a black body, which we'll talk more about in a second, it produces radiation at a particular electromagnetic radiation at a particular wavelength. At longer wavelengths, cooler things like the Earth's atmosphere and ocean also emit electromagnetic radiation, but it's not visible to us because it's much cooler temperatures that are emitting it than the sun's temperatures. And so it comes out at much longer, rather than sometimes the solar radiation is called the shortwave radiation, and this is called the long wave radiation. But so this energy that's absorbed gets re-emitted back as long wave radiation, which might go back out to space, might go downward towards the surface, might go upward from the surface towards the atmosphere. So it's bouncing back and forth in this cycle of radiation and back radiation, back and forth and back and forth. Some part of this escapes through the clouds and greenhouse gases, which also block. Greenhouse gases affect these longer wavelengths, but not these shorter wavelengths. So greenhouse gas, there's a window, a small part of it goes out here, and so about 239 watts per meter squared goes outward as in the form of long wave radiation. 341 minus 102 minus 239 is 0. So this is actually a very close to closed budget. It's not closed at the moment because of global warming, which makes this number a little bit smaller. And also affects this number through albedo. But this is the primary direct effect of greenhouse gases to change this number. If these three don't balance, what happens? Well, we've got more sources than sinks, which means our energy content of the Earth is going to go up, which means in fluids like the atmosphere and the ocean, in order for the energy, internal energy to go up, that means their temperature goes up. There are also important energy exchanges between the atmosphere and the ocean, things like evapotranspiration from the plants, thermals from hot air rising, the air that's being heated at the surface and rising, or latent heat exchanges of precipitation and evaporation. The latent heat is the heat that's stored in steam beyond water vapor, beyond its temperature. So when you boil water, it actually takes more energy to convert it from liquid to vapor than it does to heat it from 0 degrees Celsius, that's very, very cold, ice cold water, to 100 degrees Celsius where it would start to boil. So the latent heat is the part of the change in phase, the energy that's associated with that, from liquids to gases and solids to liquids. And so if you add up these down here, this is actually saying that the net absorbed is about 0.9 watts per meter squared. So that's the global warming signal as of this estimate. Okay, let's talk a little bit more about long wave and short wave radiation. When a emitting hot body emits electromagnetic radiation because it's hot, it does it as a factor of its temperature. And so hotter things like the sun emit at shorter wavelengths and actually have more area under the curve, which means more power emitted. The Earth, which is much cooler, is at longer wavelengths and has less area under its curve. So the point here is the sun is emitting more energy and is emitting it at shorter wavelengths. This is called, there are a bunch of different laws about this. This is basically called black body emissions. The Earth and the sun are not exactly a black body, but they're approximately so to a reasonable degree, which means that we can still think about these curves and understanding how they emit infrared and visible radiation based on their temperature. We've already talked about albedo, but that's the reflectiveness part. And the albedo isn't fixed because things like the cloud fraction changes. This is a map of cloud fraction for 1 month, 2010. And you can see there's an awful lot of clouds. Clouds affect albedo, greenhouse gases they don't affect albedo, but they affect the energy budget too. So in turn, the heating affects both the clouds and the greenhouse gases. So there are feedback loops that are present in this Earth system, which is an important part of how sensitive the Earth is to climate change. Here's one good example of a feedback loop. If we warm the surface temperature, that law right here would make the Earth go a little bit more like the sun. It would get a little bit longer wavelength. It would get a little bit more area, so it'd be emitting a little bit more radiation. So a warmer surface temperature leads to more outgoing infrared radiation, which then would cool the surface. And so if it's warm makes more, but more makes colder, this is a negative feedback loop. So this is negative sign is indicating that. So area under the curve goes like the temperature to the 4th power. This is called a Planck function. And so if we change the temperature like this, we're changing the area under the curve, and we're also changing the peak towards shorter and shorter wavelengths. So this is the kind of budget that we think of for the Earth, minus the atmosphere, minus the ocean feedbacks. But an interesting alternative is something like the ice albedo feedback, where warmer surface temperatures let's do it colder, because that's what this color is. Colder surface temperatures lead to more snow and ice cover, which leads to a more reflective albedo, which leads to colder surface temperatures. This is a positive feedback loop where a cold leads to snow, leads to reflection, leads to more cold. If we flip it the other way, it does not reverse. It's still perturbation leads to more perturbation. Warm leads to less snow, leads to more absorption, leads to warmer. So either way we go, we get a positive feedback. And positive, in this sense, I mean it's amplifying of the initial perturbation. Negative is damping of the initial perturbation. That's what I mean by positive and negative feedbacks. So there's a greenhouse. I won't talk too much about greenhouse gases and greenhouse effect, but these are part of your climate literacy that you should know. If you are not totally clear on what these things are, I would recommend you come back here, pause, and read these two definitions from the IPCC carefully. Another positive feedback, maybe the most important positive feedback in the Earth system, is the water vapor feedback. And this one directly relates to the ocean. So water vapor is the most important greenhouse gas on Earth, not only because it absorbs most of the outgoing radiation, more than carbon dioxide, more than chlorofluorocarbons, more than methane, but also because it responds to the surface temperature changes. This is what I mean. If you warm the surface, you're going to evaporate more, which means you're going to have higher atmospheric water, which is going to make a stronger greenhouse effect, which is going to warm the surface even more. Warm, moist, warming, warmer. Cold, dry, less warming, colder. So it's positive feedback in both directions. If there's an imbalance in either of those budgets, then you would get a change in the amount of stuff in the system. And in this system that we're talking about now, it's a change in the energy per unit time. So warming, global warming, is a result of a heating imbalance. Global warming, or if you want to think of it as change in the latent heat, it could be a global moist. Electromagnetic flux, this is a little bit of a math to think about what the sun's like. And so that 341 is actually not a good estimate of how much is arriving at the Earth, but not all of the Earth's surface is exposed to the sun at a time. So you end up having a slightly decreased by average radiation to the surface because of the way that this works. Okay. But is all of the Earth's surface heated the same amount? Well, no. I mean, look, the sunlight is more direct here, and what counts is the amount of energy per unit time in an electromagnetic wave that passes perpendicularly. So this larger area, where this ellipse is, only gets the amount of energy that this smaller area does at the tropics. So there is actually less energy per unit area solar being delivered near the poles as there is near the equator. And in fact, this is particularly true in the polar night, where for the whole winter season you don't have direct sunlight, so you don't even have much sun coming in. Whereas in the polar day, there's sunlight year round, or sunlight day round. So you get a lot of sun, but it's very indirect sun. So its amount of energy per unit area is quite low. Whereas the latitudes of the Earth that are getting direct radiation are getting a lot of radiation, a lot of warming per unit area. So if you think about how that works as a function of latitude, you get a picture that looks something like this. The tropical latitudes between about 32 north and 32 south tend to have a surplus of incoming solar radiation over the amount of outgoing long wave radiation they emit. So these latitudes are net warming. On the other hand, the poles, the latitudes farther north and south of these 30-something, tend to have a deficit. They have more emissions of long wave radiation than they absorb in solar radiation. This is the annual mean picture. If we were to show you a seasonal picture, it kind of wobbles back and forth between the different hemispheres. From the summer hemisphere receiving more of this surplus, and the wintertime hemisphere receiving more of this deficit. So how does that work? Does that mean that the tropics just get warmer and warmer and warmer and warmer? Well, no, it doesn't. This is still an equilibrium or steady state situation. So what must be happening is that there's heat being transferred from these surplus regions toward the deficit regions. So part of the energy, and more than enough energy to warm the tropics, is arriving from the sun. But some of that energy is actually not heating the tropics. It's being transported out towards the poles, where it's making up for the deficit in terms of the solar radiation versus the outgoing long wave radiation. Think of it like this. There's a net energy transport required away from the tropics towards the poles. Well, so what is the agent of this energy transfer? Well, could be a lot of things.
The first law of thermodynamics. Heat is work and work is heat.
Heat is work and work is heat.
Very good. The second law of thermodynamics. Heat cannot of itself pass from one body to a hotter body.
Heat cannot of itself pass from one body to a hotter body.
Heat won't pass from a cooler to a hotter.
Heat won't pass from a cooler to a hotter.
You can try it if you like, but you far better not.
You can try it if you like, but you far better not.
Cause the cold in the cooler will
And here we get to the ways that energy can be transferred.
body's heat will pass through the cooler.
Cause the hotter body's heat will pass through the cooler.
Heat is work and work is heat and work is heat and heat is work. Heat will pass by conduction.
Heat will pass by conduction.
Heat will pass by convection.
Heat will pass by convection.
Heat will pass by radiation.
Will pass by radiation.
And that's a physical law. Heat is work and work's a curse. And all the heat in the universe is gonna cool down. Because it can't increase, then there'll be no more work and there'll be perfect peace.
Really?
Yeah, that's entropy, man. Law.
All right, so after that interlude from Flanders and Swan, we will note that this basic sense of how energy can be transferred by radiation, convection, conduction, or latent heat. We add latent heat to the story because we're thinking a lot about the transfers of water and different forms of water. Those different pieces of the story is how the energy gets around. So that heat transfer that we needed could be carried by conduction, convection, radiation, latent heat. How does it go? Well, part of what's happening is that there's convection, so the movement of air and moisture, and the energy flows. Sensible heat transport means that we just take the warmer air and we move it toward the poles. Or we take the warmer water in the ocean, we move it towards the poles. That does some work. But you also can take moister air and move it over here and then precipitate it out. Take moister air, precipitate it out. That also transfers energy. So moist air flows poleward, dry air and liquid water in ocean currents and rivers flow equatorward, hot winds flow poleward, cold winds flow equatorward. That's the way we transfer energy. There's not a whole lot of conduction worth thinking about. It's in turbulent fluids, the conduction tends to be a very small part of the transport, and actually the only real conduction we could have would be in the solid Earth, and the solid Earth doesn't conduct that much enough heat, at least at the surface, to make a difference in this kind of budget. Okay, so where then is this heat flux? This is a measure, or it's actually an inference from a bunch of measurements of the heat. And so you can see the heat is actually, this is oceanic transport of heat. The colors are showing you where the heat is coming in. So the ocean is being warmed in these yellow and orange spots. The ocean is losing energy in this blue spots. Over the Gulf Stream and Kuroshio, there's a whole lot of energy being lost. And over the tropics, there's a whole lot of energy being gained. And you'd imagine that it'd be little arrows that'd be pointing from these hot regions to these cold regions, and there does seem to be. So that's the transfer of heat. One very interesting reason, which we're going to talk an awful lot about, is the fact that the these little arrows all point northward in the Atlantic. That's something that's a bit of a surprise. So here's where the sun comes in. So part of this heating of cooling of the surface is solar. Here's the solar map, and as you'd expect, it's higher in the tropics, lower at the poles. We already talked about that, and it includes the albedo effect already, so you can see that there's a difference between the solar over land and the solar over water as well. Here's the outgoing from the atmosphere, so outgoing long wave radiation. This is the top of atmosphere outgoing, and this is a more complicated pattern because it has some absorption effects, it has some land sea temperature difference effects. There's a lot of pieces in this story that makes it a little more complicated. And there's also cloud effects here too. And so here's the net to the atmosphere at the top of the atmosphere. So what can the atmosphere do with this? Well, it could take it away from this net region, or it could dump it down into the ocean. And so here is that map from that same, here's the mean of this figure, which is that same map. So here's the excess of tropical, and here's the deficit of polar. And here's what the atmospheric transport looks like. The atmospheric transport transports northward in the northern hemisphere and southward in the southern hemisphere. So from here to there, that's this hump. From here to there, that's this hump. And here is the required transport in the solid line. And then these two dashed lines are two different atmospheric model estimates of how big this is. And so there's something left over, some missing energy transport. So that must be getting carried by the oceans. And if we infer how much the oceans take, this is their curve, roughly 2 petawatts of heat transport at the peak. In the northern hemisphere, 1 petawatt, and in the southern hemisphere for this data set, and in this data set it's more about 1.5 to 1.5. Kind of interesting that they're quite different. There are more updated estimates than these, which I could be showing, but these are the ones we have from this nice paper by Trenberth and Karen, which really laid this out. And one of the reasons I really like this particular paper's version is that it not only shows the total of the oceans, but it shows it broken down by basin. So here's the Indian Ocean, which makes up a good fraction of this southward heat transport. It doesn't have a whole lot of northward heat transport because there's not a northern Indian Ocean. This is where the Indian Ocean stops. The Pacific Ocean looks an awful lot like the atmosphere, this green. It has a northward energy transport in the northern Pacific and a southward energy transport in the South Pacific. But here's the Atlantic. And look, it's just positive everywhere. So this magic is what we're going to talk about when we talk about the meridional overturning circulation and the Gulf Stream and the North Atlantic Deepwater, which we already hinted at a little, is the agent, and the Southern Ocean water masses is the agent of this northward heat transport. If we think about the fluxes from air to sea, we can break them down into shortwave, that is solar, the net, this is the net heating of the ocean, and sensible, which is hot water making air hot, long wave, the outgoing long wave, and latent, which is the evaporation and precipitation effects. So you can see that the sensible effect, which might have been the one you were thinking of when you were first thinking of this, is actually quite small. The big players in this game are the sun's heating, the long wave cooling, and the latent heat exchange, so evaporation and precipitation at the ocean surface. In map form, this is what they look like. Here's the air-sea flux, the net, here's the shortwave, here's the latent heat flux, and here is the precipitation and river runoff as well. So freshwater and energy. These are what the maps look like. And for those of you who've taken atmospheric dynamics or who are into weather, you might recognize some of these patterns, that the freshwater fluxes are large in the intertropical convergence zone, large in the upwelling regions, very, very low in the subsidence regions, these dry desertification regions, and then somewhat larger again as you get to the north, to the northern mid-latitudes and southern mid-latitudes. this picture makes it seem like we really understand what's going on, but actually these fluxes are not very well known from point to point because they are extremely variable in space and time. So here's the standard deviation of the annual shortwave, and here's the standard deviation of the sensible long wave, latent. These are big numbers. These are 50, 30, 60, 30, 70 watts per meter squared, which are rivaling the gradients on these kind of large scale in between the different sources and sinks. So there are big terms canceling in the types of radiation. That's what this figure shows. There are big terms canceling from place to place on the Earth. There are big terms canceling in the time of evolution of these terms. And this is just a way of showing this is the annual cycle and this is the interannual cycle. So El Nino and things like that on interannual timescales also affect these fluxes. I'm not going to talk too much about the freshwater volume except to say that it's roughly consistent with that story. What about the momentum fluxes? You might be saying, well, okay, we talked about heat, we talked about salt, we talked about volume, we talked about, what about momentum? So wind stress, a stress is the rate of momentum transfer. The wind stress is the rate of momentum transfer from the winds to the ocean, or actually alternatively from the ocean to the winds. It's more difficult to think about than heat and freshwater because it's directional. But we can take a quick look now, but we're going to spend a lot of the semester thinking about how winds drive the waves and currents. So here's a map, which is a little different from the one that we showed. This is the stress exerted on the ocean by the winds. And so here is Pa, and so I'm not reading that color bar right. Colors give the base 10 logarithm of the strength in newtons per meter squared. Oh, okay. The arrows are giving us the direction, and this is a logarithmic measure of strength. So the Southern Ocean's really got a whole lot of winds. The tropics have pretty good winds. Up here near Greenland, there's a lot of winds. And then these lower wind regions are not just a little bit lower. These are 2 orders of magnitude lower than the orange region here. So there's a lot of variability in the pattern of winds, but there's roughly westerlies in the roaring 40s of the southern and northern hemisphere. Then there are easterlies right at the equator and kind of transition zones in between. We're going to talk more about the direction of the wind and how that influences the way that the currents go. But the winds, too, are extremely variable. Here's the logarithm of the ratio of the kinetic energy and the variability of the wind field to that of the time mean. So this means, this color right here, this breakpoint between green and green means that the variability is 10 times more energetic than the mean. And look, that's a pretty common color. Or these red colors are even more common. So you start to see in these storm track regions, the variability is quite a bit more, it's quite a bit higher than the mean, which means that we maybe shouldn't be thinking the winds as steady, although at least in these parts of the world. But we're still going to use steady winds to understand how the ocean responds in the basic case. We'll think a little bit about unsteady winds when we get to the end of the semester and talk about waves. Here are the time scales of that variability from maybe half a week up to maybe 3 weeks, with particularly long time scales in the Indian Ocean, which is interesting for a variety of reasons. There's a monsoonal reversal, which has a lot to do with this, but there are also these relatively long intra-seasonal, they are called, variability within the Indian Ocean that does a lot of variations. The wind stress curl, that is the derivative of the wind stress, is a really important quantity for us. And you can see, unlike the wind stresses, which have these relatively large scale patterns, the wind stress curl has these little rivulets inputs in it, and some of these are actually permanent features. These are swirling patterns of the winds on the surface of the ocean. So just like we talked about the vast and diverse figure, here's another one from Mark Barrasa's paper, and this is the vast and diverse figure, but color-coded by the amount of errors in fluxes you could allow into each of these. So here we go. So climate change needs to be accurate to within about only 0.1 watts per meter squared in order to be accurately calculated, and ice sheet evolution within about 1 watt per meter squared. So these are really pretty challenging. These colors in here are really quite challenging to get right from an energy budget perspective. Mesoscale, short scale physical biological interactions are actually pretty robust, even pretty big errors in the fluxes. Ocean upwelling and annual ocean heat flux variability, those also are pretty robust to errors. So the motions of the atmosphere and the ocean are part of the meridional redistribution of heat that rebalances the radiation imbalance by latitude. The ocean overturning, gyres, and atmospheric cells all contribute. We're going to learn exactly how they work, what drives them, and why they're there. But they contribute to this heat transport. So in the big picture, motions of the oceans are redistributing heat. They're helping the atmosphere do that. And they're there because of these differential heat budgets and differential wind stresses. So momentum, essentially, budgets across the Earth.